Right now, literally as we speak, invisible, high-speed secret codes are protecting our entire digital world. Every single time you send a text, check your bank balance, or even just connect your wireless headphones, there is a silent, complex mathematical battle happening right beneath your fingertips. Today, we're decoding the mystery of encryption, and we'll be pulling from some great Cambridge IGCSE computer science material to do it.
Take a look at this wild, glitching string of symbols. These strange, alien-looking shapes perfectly represent the core problem of digital communication. Think about it. If I want to send you a private message across the vast, entirely public network we call the internet, how do I stop everyone else from reading it? Because when data travels from your device to a server, it bounces through dozens of routers and nodes. Someone could absolutely be listening. So this string of symbols is what we want any potential eavesdropper to see. It's called ciphertext. It looks like absolute nonsense, and honestly, that is exactly the point.
So, how do we solve this? Well, the answer is encryption. Our source material defines it pretty clearly. Encryption simply means changing information into a secret code. You're basically turning readable data into that unreadable ciphertext we just saw, so only the right person can read it. It's kind of like the ultimate digital disguise. You take a plain, readable message like, hello, run it through a complex mathematical algorithm, and spit out a scrambled mess. But it's not just a random mess. It's a carefully engineered one that can be reversed, but only if you have the secret to doing so.
A really good metaphor for this is a locked box. Think about sending a physical letter. You definitely wouldn't write your deepest secrets on a postcard where the mail carrier could just read it, right? No, you put it in a box, you snap a heavy padlock on it, and you ship it off. That box might pass through 100 different hands on its journey, but without the physical key, nobody is seeing what's inside. In the digital world, our algorithms are the box, and data bits form the lock and the key. Okay, let's look at path 1, symmetric encryption.
This is really the foundation of digital security. Let's trace the path on this flowchart together. Starting on the left, we have your plain text. We apply an encryption process using a secret key. Actually, a great real-world example of this is AES encryption. That's what powers apps like WhatsApp. Once applied, boom, we get the ciphertext in the middle, that scrambled, unreadable code. Now the data is totally safe to travel. When it finally reaches its destination on the right, the recipient uses that exact same secret key to run the decryption process, turning the ciphertext back into plain text. One key locks the door, and that exact same key unlocks it.
Now, the really crucial point here is that this single key method is incredibly fast. Because the math only requires one key for both actions, your devices don't have to work very hard at all. This makes it the go-to choice when two devices already trust each other and are close by. Like, notice this Bluetooth pairing screen. When you pair your phone to a smart speaker or your car, you usually confirm a short PIN code, right? Well, you're essentially establishing that shared secret key in a safe, localized environment. Once they both have the key, they can blast symmetric ciphertext back and forth at lightning speed. But this brings up a classic Cambridge IGCSE computer science problem. What happens when you need to securely send a secret over a public network to someone you haven't established trust with yet?
And that brings us to path 2, asymmetric encryption.
Here is the brilliant solution to our public network problem. Asymmetric encryption basically ditches the single key and uses a two-key tag team. Notice we've got a green public key and a blue secret key, or private key. This tag team is the basis for protocols like RSA encryption. So here's how it works. The public key is used only to lock the message during the encryption phase. The receiving party can share this public key with the entire world. They literally do not care who has it. Why? Because the public key cannot unlock the box. Once the data becomes ciphertext, the absolute only thing in the universe that can unlock it and turn it back to plain text is that separate, heavily guarded private key.
So, looking at the two paths side by side really highlights why we actually need both. Symmetric encryption, like AES, is your fast, single-key speedster. It's super efficient, but it requires that both parties already safely share a key, which makes it perfect for localized, trusted devices. Asymmetric encryption, like RSA, on the other hand, is your heavy-duty two-key vault. It requires a lot more computational power and is definitely a bit slower, but it completely solves the problem of sharing data over the open internet. You literally never have to transmit your unlocking key. You just hand out your locking key to anyone who wants to send you something securely. To see why this matters, and to solve our computer science problem, let's look at a real-world example from our sources, online banking. When you visit a bank's website and see that HTTPS in the web address, you're seeing asymmetric RSA encryption in action. Step 1, you visit the site. Step 2, the bank server hands your web browser its public key. Step 3,
Your browser uses that public key to lock up your passwords and financial data into ciphertext. Even if a hacker intercepts it right then and there, it's completely useless to them. Finally, step 4. The data reaches the bank, and the bank uses its closely guarded private key to unlock the data. It's literally an invisible shield keeping your digital life safe.
As we wrap up this explainer, I want to leave you with kind of a wild thought. Your entire digital safety, your bank accounts, your private messages, your medical records, relies entirely on the mathematical impossibility of someone guessing that private key. The math is so complex that it would take current computers millions of years to guess it. But as computers get faster and exponentially more powerful, we really have to ask, will our locked boxes stay closed forever? It's a digital arms race, and encryption is right on the front line. Thanks for joining me for this explainer, and definitely keep your keys safe.